Let's discuss the average rate of change versus the instantaneous rate of change. We're going to start with what you already know, the average rate of change. So let me start with the picture. Let's take a curve, and let's say the curve, uh, it has a quadratic pattern to it. It really doesn't matter what the curve is. We want to think about how to find this average rate of change. So if we had just a straight line, we would know how to find the rate of change of that straight line. It is just simply the slope. So for instance, if I had a straight line from here to here, we could find the rate of change of this line. It is simply the slope. But the problem is when I have that curve, I can't just find the slope. There's not one set slope value. So for instance, here at this point, the slope might be close to a half versus considerably further along the line, or the curve rather, the slope might be closer to 2. And so we can see that rate of change is never constant. It's always changing, unlike with the line. So what we have to do is we have to look at an average. So if I wanted to find the average rate of change between this point right here and this point right here, we could do so using this line right here, and this line is what we call the secant line. The slope of the secant line will always give us the average rate of change. So let's put some values to these. Let me put this on a XY plane. So again, I just kind of have it floating in space right now. I don't care exactly what the curve looks like. But we'd have an x1 and we'd have an x2. And of course, we'd have some y values associated with those. And if we're using our function notation, at that x1, we can find its y value, f of x1. And then at that x2 value, we could find its y value, f of x2. And so if we wanted to find the slope, or the average rate of change, which I'll abbreviate ARC, not to be confused with ARC, it's just an abbreviation for average rate of change, we could do that by calculating slope, which we know is y2, and the y2 was the f of x2, minus y1, which would be f of x1, over x2 minus x1. Average, we always are looking at those 2 points, and we're saying, well, between them, what does the slope of the secant line look like? And so if we were to take an example of this, I just drawn out a quadratic function, so let's take f of x to be, make it 2x squared plus 1. And let's find the average rate of change between 1 and 3. So I need to start by finding those f of x values at 1 and 3. I'm going to look at f of 1. I'm going to look at f of 3. So of course we just plug those in. F of 1 we'd have 2 times 1 squared, which is 2, plus 1 will give me 3. Then f of 3 we'd have 3 squared 9 times 2 is 18, plus 1 is 19. And so now we have all the information we need to find the average rate of change. It will be 19 minus 3 over 3 minus 1. 19 minus 3 would give us 16 over 2, which is equal to 8. And so our average rate of change between these 2 points would be 8. Pretty straightforward. It doesn't matter if we use a different function name, but the formula is just the same one that we're accustomed to from finding slope. Now, that is something we've seen in the past because we've done lots of problems with slope. The instantaneous rate of change is something we've never been able to do in the past, because now, if we look at that exact same curve, now I want to know what's going on at this one single point. And that's a problem because if we look at our formula relies on 2 different points. It has to have the x1, x2, y1, y2. And now we only have a single point. So I'm going to use a similar idea. I'm still going to use that slope formula, but I'm going to have to drive the 2 points infinitely close to one another. And what allows us to get infinitely close to things, or far away from things too? What we've been studying most recently, limits. Limits give us that ability to not just look at what happens at one single point, but what happens as we approach that point. So what I'm going to do first is, this is a little bit cumbersome to work with when we're working with limits. We can use this formula, but I'm going to come up with another formula for finding slope first that will make it a little bit easier to apply those ideas of limits. Now, rather than thinking about this as x1 and x2, I could say, well, I simply want to know the distance between these 2 points. How far have I moved? And I'll call that distance h. And so now, rather than writing x2 minus x1, I've already calculated that distance as h. And that's going to change my y variation a little bit. Let me define this initial point as x. And so that means our y1 would occur at f of x. And as we've had it set up, now to find that f of x2, it's not x2, it's whatever we started at plus how much we've changed by. And so we can redefine this f of x2 as f of x plus h. It's the exact same formula, it's just I've kind of reparameterized things. Rather than saying, let me view a point 1 and point 2, I'm saying, let me view a starting point. Let me say this starting point is x, and then I'm just going to define some variation from it or some distance away from it by h. And that's going to take me to a second point. Don't really care what that second point is called. I'm just going to call it a distance away of h. And so I know the change in the x's then is h, and that means when I go to find the y values, my initial y value is f of x. That's my starting point. My terminal position is whatever the x plus h is, or f of x plus h will give me that second y position. And the reason this is nice with limits is because it allows me to kind of ignore the points themselves, because we're only looking at that one point. We only have that one initial starting point. And we do, in order to calculate the slope, we do have to have a point away from it as well. But I don't want to define that point because I want to shrink that point down to being infinitely close to my initial point. So this just gives me a very convenient notation to do so. And so now what we're doing is we're looking at what happens at this single point right here, and we're looking at the line. We still want to calculate a slope, that's the rate of change, but we're looking at the line that would pass through only that one point, and that line is called the tangent line. So the secant line is a line that connects the 2 points, giving us an average rate of change. The tangent line is a line that kind of brushes up on our curve, but doesn't actually pass through it again in that immediate vicinity. Now, of course, if this function were to carry on later on, maybe the tangent line passes through it, but I'm just looking in its immediate vicinity at how many times does that line pass through, and it should just be the one time. It should just touch and skirt off of it from there. So if I want to calculate that instantaneous rate of change, I'm going to have to use this same slope formula, which we've redefined like this. So I'll have the f of x plus h minus f of x over h. Because we have to have some distance away from that first point. We can't have the 2 points being the same. We'd have 0 in the denominator. But we'd really love to drive that 0 we'd love for it to be a 0 in the denominator in terms of being infinitely close. We'd love for those two numbers to be super close to one another, but it can't actually be 0. So how do we drive those 2 points infinitely close to one another? We take a limit. We're going to let the h go to 0, meaning we're driving the distance between these 2 points to 0. We're getting them infinitely close to one another, but because it's a limit, we're not actually saying that denominator is equal to 0. And that will give us that instantaneous rate of change. So let's take the same problem we did just a second ago. We had f of x is equal to 2x squared plus 1. And this time I'm going to find the instantaneous rate of change at 2. Now it might be pretty close to what we found the average between 1 and 3 is. It might be pretty close to 8. It might not be exactly the same. We'll find out in just a second. So if I want to find the instantaneous rate of change, we're going to be taking a limit as h goes to 0 of this thing right here, and this should look familiar to you. We've named this in the past, even though we never actually did the limit with it. This right here is what we call the difference quotient. So we're taking the limit of the difference quotient. So we should be familiar with this process. F of x plus h is telling me I need to plug the x plus h in for my x. Then I'm going to subtract from this is my f of x plus h, subtract from this my f of x, which is 2x squared plus 1. I'm going to divide this by h. So we do need to be comfortable with that difference quotient. I do expect us to already be pretty comfortable plugging into that. Do keep in mind the parentheses around the second half are absolutely necessary. When I put the parentheses around the f of x plus h, that was merely for effect, so we can see this is our f of x plus h. But here, the f of x, I've got to keep that in parentheses because we have to remember to distribute that subtraction. So now we're just going to simplify. So we have to remember, anytime we see the squared on this binomial, we have to FOIL it out, or we have to fully distribute, or we do have a shortcut for it. We square our first term, we multiply the two terms and double it, so we have a 2xh, and then we have our last term squared. We have the plus 1 there. I'm going to keep all of that in parentheses because I have the 2. The 1 should not be inside. Let me correct that. Sorry. The squared portion, I end after the h squared. That was being multiplied by the 2. Now I have the plus 1, but I need to keep that initial half in parentheses because I have to distribute the 2. If I want to keep the parentheses around the 2 and the 1, I can. Don't need them. But then the f of x, I am going to keep the parentheses around that until I either distribute the negative or go ahead and subtract. And so you can distribute this if you like. I think a lot of times it's easier to leave it in parentheses because then it makes it easier to see the like terms, but it doesn't matter. And just like when we were finding limits earlier, notice I'm writing that limit statement every single step because I haven't actually found the limit yet. And so now let me actually distribute the 2. So we'll have 2x squared plus 4xh plus 2h squared plus the 1 minus the f of x stuff still, all over h. And now I can simplify some things in the numerator. So the 2x squareds, those will cancel. The 1s, they will cancel as well because we have a 1 and we have to remember this is really a minus 1 here. So this is what I mean. If you want to distribute that in the previous step, you can. I just sometimes think that having the minus in front it makes it easier to see the terms match up. Doesn't matter, whatever you're more comfortable with. So now what we have, still have our limit in front. And on the numerator, we have 4xh plus 2h squared over h. And now we can cancel out the h's because every single term has an h. We can cancel out one h from every position. We couldn't do that before because we had those x squared terms and the 1s. Couldn't cancel out the h's, but we can now. So we have the limit as h goes to 0 of 4x plus 2h. And so as h goes to 0, the 4x, even though x is a variable, it's not a variable in terms of what the limit is considering. The limit is only looking at h's moving. So we consider the x to be a constant. Therefore, we get 4x back out of the first half, and then 2 times 0, of course, would just be 0. And so our limit would be equal to 4x. Now, we actually wanted to find this instantaneous rate of change at 2. Or at x is equal to 2. So the last thing to do is to plug in that 2. When I do that, notice I get the same 8 that I did just a second ago. So my instantaneous rate of change at 2 is 8. Now I will point out something here. I did this problem in complete generality. I left all my x's as x's from the start. I did not have to do that. If I wanted to, in that very first line, I knew I wanted to evaluate this when x was equal to 2. So I could have replaced all these x's with 2's. And it would have cleaned up a little bit nicer from the start. We would have had the limit as h goes to 0 of, we would have left the 2 in front for a second. I'm going to go ahead and multiply this. Again, we're kind of ignoring the x's, or what we've done is we've replaced the x's with 2's. So I have a 2 here and I have a 2 here. So let me real quickly multiply this together and simplify. So we'd have 4 plus 4h plus h squared plus the 1, and I've switched over to green for no reason at all, minus the 2 times, well, 2 squared is 4 plus the 1, still over the h. We can write this as the limit as h goes to 0 of, we're going to distribute the 2, so we'll have 8 plus 8 h plus 2h squared plus 1. Then here we have 2 times 4, which is 8, plus 1 will give us 9. If we want to simplify it, we can, or we can kind of subtract first, doesn't matter, all over h. So what I notice is I have those x squareds and constant terms canceling with the f of x, same way we did before, it's just now we actually have numbers in those positions. And what I have left, I have the 8h plus 2h squared over h. Well, just like we saw a second ago, the h's are going to cancel, leaving me the limit as h goes to 0 of 8 plus 2h. And as h goes to 0, we are left with an 8 here. So it didn't matter which of the two ways we did it. The first time I treated everything just as the x. I didn't actually plug that x in right away. And that's fine. It's doing it a little bit more generally, and then we're plugging in at the back end. Or because we're actually evaluating an instantaneous rate of change at a particular point, I could actually plug that number in. I think, especially in our beginning stages, we're much more comfortable with this just because we're more comfortable with numbers. And so if you want to do this initially, that's fine. Long term, we do want to move to more of this method. The advantage to doing it this way, for one, maybe I ask you to find the instantaneous rate of change at 2, 3, 4, and 5. Well, do I really want to have to do this whole operation for 2, 3, 4, and 5? Or would I rather just do this whole simplifying step once? I find that I have my simplified difference quotient with the limit, and then I can plug in the 2, the 3, the 4, and the 5, and it becomes very easy to do. So doing this operation with the x's in generality, even though it's a little bit more complex at the front end, can make our life a little bit easier. Now we're going to have a name for this thing right here. It's not just an instantaneous rate of change. I'm not going to name it quite yet because I want to talk about some other things first. But we'll come back to this idea, why do we want to leave it as an x? Well, keep in mind, I'm saying there's going to be a special name we give this thing in just a minute. But before I do move on to that, I want to talk about the fact that we just ended up at 8, which was the exact same as our average rate of change. Are those always going to be the same? Not at all. No. Obviously, if there's a reason we're doing all this extra work, it's much faster to find that average. Why can't I just always take two numbers around it and split the difference? Well, that doesn't always work. This was a quadratic function, and quadratic functions have kind of some special properties that allow that to happen a little bit nicer than other functions. So we're going to look at another example in just a second, that an average rate of change is going to give me a very different answer than an instantaneous rate of change. The x squared function has just a special property to it. Just the way that it is, it works out that a lot of times when we split those average rates of change directly around the value we want to look at the instantaneous rate of change, they might give us the same, but that is not a guarantee for all functions. So this time, let's take g of x to be the square root of x plus 3, and the plus 3 is on the outside. I want to find the average rate of change between 1 and 9. And if we think about what would be halfway between those two values, that would be 5. So let's look at the instantaneous rate of change at 5 as well. And so I'm going to do both of these problems. We'll see if we get the same number. Well, with the average rate of change, remember we need the G1 and G2. In this case, when I say G1, G2, I mean the Y1, Y2. So I need the G of 1 and the G of 9. So we plug in 1. Square root of 1 is 1 plus 3, we get a 4. Square root of 9 is 3 plus 3, we get 6. And so for my average rate of change, I'm going to take the 6 minus the 4 over the 9 minus the 1. 6 minus 4 is 2, 9 minus 1 is 8, and that gives us 1/4. Now my instantaneous rate of change, I'm going to go ahead and plug in my x value because for right now, I'll just show you the other way of approaching the problem. So the instantaneous rate of change, we have to use the limit of the difference quotient. So I'm going to take the limit as h approaches 0. I'm going to take the square root of my x plus my h, and again, we're going to go ahead and plug in the x this time just to kind of illustrate the other way we can do it, minus the square root of the 5 all over h. And so if I look at this problem, I'm getting 0 in the denominator, and I'm also getting 0 in the numerator. And in a previous video, we talked about the fact that this is, we're later going to define it as being an indeterminate form. The book hasn't defined it as such yet. But anytime we get that 0 over 0 when we plug in the h, that is indeterminate form, but more importantly, it's telling me something else needs to be done. And so for a problem like this, what we can do is we can always rationalize the numerator. Kind of our trick when we have square roots involved and we're getting 0 over 0, we want to multiply both top and bottom by the conjugate. And so I'm going to be multiplying my initial by the square root of 5 plus h plus the square root of 5. And so when we clean this up, let's see what we get. We need to remember to fully distribute. So we're going to have the limit as h goes to 0. When we multiply the radicals to one another, they just cancel, giving us what's on the inside. So we'd have a 5 plus h. Because they are conjugates, the center terms will cancel. We'd have root 5 times root 5 plus h minus root 5 times root 5 plus h. They will cancel. And so then we have to multiply those last terms. We'd have the root 5 times root 5, giving us just a minus 5. And then on the bottom, we have our h times the square root of 5 plus h plus square root of 5. And now we see that these 5's cancel. And once we see that those 5's cancel, well, now we have some like factors. We have in the top just an h. And then in the bottom, we have an h times the square root of 5 plus h plus the square root of 5. And so now the h's cancel. And we're going to be left with the limit as h goes to 0 of 1 over the square root of 5 plus h plus the square root of 5. And now we can plug in the 0 for our h, and we're not going to just get a 0. We're going to get limit as h goes to 0 of 1 over, and we would have square root of 5 plus the square root of 5. I can drop my limit at this point. Don't need to keep that because I already plugged in. And so we'll have the square root of 5 plus the square root of 5, or 2 square roots of 5. And that looks very different than 1/4. It is a different number. It would be close. And so if we wanted to see what that would be, let me just type in my calculator real quick. So 1 divided by 2 square root of 5 would give us approximately 0.223. It is an approximate. So, we had a quarter before, which would be 0.25, and so we're close. But it's not the same thing, and that's my statement coming from the last example, is the instantaneous will not always be the same as the average. And the more focused we are on that point, so 1 and 9 relatively close to the 5, it's going to be better than if we were, say, using I couldn't go any lower than 1 because I'd have undefined values, but if we're looking maybe at the instantaneous rate of change at 100 and I chose 1 and 200, probably not going to be as accurate as when we're getting those closer ranges. Obviously, if we have a curve, the closer we are to that point, so let's say we're looking at the rate of change at the point in red, the closer we are to that, it's going to be much more accurate than if we're much further away. This point over here is a lot less accurate indicator of what's happening here than the points immediately around it. So if we're trying to use an average rate of change to approximate an instantaneous rate of change, it will be a decent approximation as long as our points are actually close. But the safest way to get that instantaneous rate of change, or the actual way to do it, is to get immediately close to that point, and we do that through using our limit. Now, one last idea I want to throw at you before I end this video. The instantaneous rate of change, I told you that this is going to have a very special name, and that name is a derivative. What we have just found is a derivative. So we'll see a stronger definition of this in later sections, but a derivative is the instantaneous rate of change. A derivative is a slope. It's a slope at a point. And so if we hear instantaneous rate of change, that is the same as derivative, that is the same as the slope of a tangent line to a point. All three of those ideas are the exact same. But derivatives, we're going to see where we want to find derivatives at points like we were doing here. Sometimes it's going to be important, however, to find the derivative in generality, and that's what we did in our first example where we left everything in terms of x. That 4x would be the derivative of the function 2x squared plus 1. And so now that we have what we've done essentially is we've created a whole other function. We've created a derivative function of the original function. So this new derivative function can be used to find the instantaneous rate of change at any point.